Last two talks of the day. Here we have Shams. He's a free diver. Who knows what free diving is? Anybody? Anybody knows what free diving is?
There are a couple of friends.
You want to explain what free diving is, Shams?
That's okay.
No.
Is it connected?
You're on.
Okay. So free diving is considered a sport by some, not a sport by some, but it's basically a form of diving in which you don't use any diving equipment. That's how it differs from scuba. So you are free, literally like a fish, and you swim inside water.
Which sounds pretty simple, right? Except that when he says that he goes down 9 meters deep, that's like about 30 feet for about 2.5 minutes. You have to be careful to come back up in time, otherwise you're in serious trouble. When he's not swimming, our man is a scientific computing expert and a mathematical researcher at Blipper. And he solves a lot of scalability and availability problems using distributed computing and architectures. Over to you, Shams.
Okay, so like I said, I do a lot of mathematics, and over the years, problems that I worked on required more or less similar things that we do in industry. It's just that we used to do that long back in academia. I tell you something about back in the university. One of the problems that I was trying to solve, it was into quantum mechanics, and it would take 2 weeks, 3 weeks, 4 weeks, or even a couple of months to run. And you would require several CPUs and several hundred MBs of RAM. It's called high performance computing by some. There are variants in industry. The names they use are like grid computing. Nowadays, a similar term, cloud computing is also used, but it's basically similar things. Difference between the way high throughput computing differs from all of this is you run your services for a very, very long time. It's not in weeks. Usually your services run continuously for months. What that requires is that you also utilize your hardware very, very efficiently. To sum up, what really high throughput computing is, AWS has written a document. It's about high performance computing, but they also define what really high throughput computing is and what are the subtle differences between the two. So the 2 points they use to define HTC are non-local load balancing, which means, let's say, if you have n number of nodes running n copies of your application, the load balancer will dispatch, depending on what algorithm you use, the request that is coming into any of the available nodes. And each of the nodes are expected to behave exactly in the same way, right? So no difference in the output. And second is you should also have some form of dynamic resource scaling. Now, when I was at the university, we used to do mostly something like this. We would request, we had a cluster of over, I think, 1,040 CPUs and about 1 terabyte of RAM. And I would say, I would register with the administrator that from this day to this day, I need about 4 CPUs, each of 4 cores, so 16 cores, and let's say 50 gigabits of RAM. That was mostly similar to what AWS later on provided on a commercial level. And this is before AWS or any other vendor came into picture with some similar services. The only difference is we were running scientific Linux at that time, which didn't have dynamic scaling. But the problems that were valid for us then are valid for commercial computing users who use platforms such as AWS or any other vendor. And the main problem is, how do you utilize, because you're paying for the hardware that you are renting, you're paying for it, and you want to utilize the hardware to the maximum. How do you ensure that you're not wasting or leaking money is the main concern. And not only that, leaking resources can also cause some other kinds of issues. Like someone was asking, over a period of time, application runs, it starts at few megabytes, but then it gets killed after it uses several gigabytes of RAM. That's a clear sign of a memory leak. So how to ensure that you don't cause those kind of leaks? why is memory a constraint really, right? I mean, everyone talks about memory as like a cheap resource, like you get it like so much now. Even there are databases which run completely off RAM, Redis, right? And it's a beautiful piece of software. Redis solves a particular problem that requires using memory to solve that kind of latency issues that it tries to solve. You have to ask a question to yourself. If you're writing an application, does it really require using RAM, or can it offload it to, let's say, some remote storage, S3 kind of block, or you can also probably say persist some things on disk, right? That answers your question. Should you be wasting memory by buffering information in RAM, or should you be using? The reason is this. CPUs generally run much faster than RAM, right? If you just keep getting your data in and out of RAM, you are wasting CPU as well. This is a very famous plot, which you would have seen like many times. I just recreated it. Recently, SanDisk wrote a blog article wherein they even challenged that in a few years from now, both network as well as SSDs will start competing with CPUs bandwidth bottleneck. CPUs are bottleneck because of RAM, and that's what they're. Well, SSD, I might not subscribe to their notion, but yes, I do agree that at some point in a very near future, networks will start exceeding performance bandwidths of CPUs, which are restricted by RAM, by the way. Okay, and this is my claim. Memory is not cheap. Start treating it as an expensive resource. So I will talk about 4 points, precisely 4 points. 2 of them are tools and 2 of them are thinking ideologies. When you design system, what should be the approach? And that is about it. So the first 2 things I said are tools, which are basically provided by Go standard toolchain. But before going into those tools, let's look at what kind of analysis can you really do with the code that you have written, right? 2 ways of analysis that you can do, or everyone does usually, is when you write the code, you analyze whether the code is correct, right? It has to at least perform what it needs to perform. And then once the code works well, you run the code, and then you see whether it performs well within the runtime boundaries that you have defined for your application. One of the things that everyone should do here is, and should be doing it, because you most likely would also have been taught this in your school, is complexity analysis. When you write algorithms, you see whether the complexity is good enough and you're not wasting excessive complexities for various reasons. Other thing is what language developers usually consider. We as application developers usually do not consider this thing, but language always considers an additional step as part of lexical analysis, what's called. They do something called escape analysis to determine whether something is something that a piece of memory that you're allocating, and this applies primarily to garbage collected languages. So let's say you allocate, you create a variable for which memory is allocated. Then you need to determine whether it is going to heap or whether it stays in the stack frame. Now this is important because stack frames are continuous blocks of memory. That means it's very predictable where the position of the next piece of memory that you're looking for is. However, in heap, it's a little different story, but it's always slower because heap is always fragmented over a large piece of memory. Another thing most people will always do is they also write tests to see if they are, their code is, doing functionally what it should do. But in Go, the nice thing is you can actually benchmark the test right as part of the testing framework that it provides. And you can, just like someone presented about CPU profile, you can also do mem profile, which shows how much memory is allocated and so on. And runtime analysis includes pprof, and there is a standard module called runtime, which provides various things that pprof provides, but within your application. I'll not go into that, and there was a very nice talk on pprof today. Okay, so the idea here is that I will go talk about escape analysis. I'll assume most people already know complexity analysis, needs no introduction. There are so many textbooks around. Escape analysis is something nice, and there is a very nice way to do that in Go. And the other thing is how do you do benchmarking and memory profiling. Okay, here's a very simple piece of code. You have a type ask, which just has one field in it, which is a pointer to an integer. And then in your program, there is another function called assign, which assigns the integer's pointer to the struct, right? So this looks like something like this. Now, if I want to do escape analysis, Go has built-in tools to do that, right? Like I said, it's pretty mature tool chain that you are working on. And to do that, you basically run go build and pass gcflex -m -l. I pass -l here to disable code inlining, but when you actually build real code for production, you should not do that because inlining is a very efficient way to speed up your program. But just to, for this particular case, it also generates a lot of text output, so I just disabled it. Okay, the interesting thing here is, which I pointed out in bold, the escape analyzer is complaining it has no idea of what P is. P is the input to the function assign. Why is that? Because I allocated the value of P inside main, and then I pass the pointer, and the function assign basically assigns the pointer to struct S without knowing what the value of that, without touching the value part of that variable. So it says it's a leaking parameter. Basically, it means it leaks out of function without really interacting with the value. And consequently, because I'm passing a pointer to the function, it has to now move this variable to the heap, right? Because now it cannot, it cannot manage the memory within its own functions stack. Okay, so it's a very simple example. To correct it, all you need to do is simply replace the pointer allocation to a value allocation, and that should solve the problem. Yes? Okay, now here's the thing. You cannot do this for everything, of course, because if you have a large struct, like let's say a struct that defines interaction with a database, for example, or maybe to a third-party system that needs buffering or that needs lots of holding data, lots of structs that it needs to hold, and so on. That's where you really do not want to use value. That's where pointer comes in handy. But for simple things like ints or floats or even strings, it might actually be better to not pass it, not put it onto heap, but actually use the stack and keep the data floating around rather than pointer being exchanged. Why escape analysis is helpful, and I give a couple of examples here. Some people would have known it, some might not, but it's rather interesting. So let's consider an array. I define an array or a slice rather, and then I assign values to. Well, one of the slices holding values of type integer. The other one is holding values of type pointer to an integer. Right? And as seen in the previous one, as you would expect, if you do an escape analysis on this, it would say that the integer j, whose pointer I'm saving inside the slice y, gets escaped to heap. Why? Because I am passing pointer to another function, right? Okay, this is rather surprising, or it was surprising to me when I first tried it, so I included it here. Instead of passing values, what about closures? Right? I create a function which is also of type value in Go, and then I pass it around. However, I'm calling the output of function closure inside main, so there is no real real passing around of the function object. So you would, and everything else, if you notice about this code, I'm not passing pointers anywhere. So what would you really expect in this particular case? Would anything get to heap, or would it all stay in stack? Any idea? Okay, someone said stack, and surprise. The moment you define closure in Go, it gets escape to heap. And there is an issue that is being tracked on the bug tracker of Go. It's open, I think, since 2014. It's low priority, but yeah, it requires rewriting some portions of the escape analyzer, so it's probably going to take some longer time. Okay, the idea of showing this is not to say that you should not use closures. Closures are very helpful and will actually help you save memory, even though it goes to heap, because if your code requires recreating a certain function over and over again, that's where you would want to use closure, and that's the best use case. But overusing it is probably not a good idea. Okay, move on to the next thing, benchmarking. Benchmarking, I think probably most people would know that Go test can also benchmark code that you write. And you can do benchmarking over time as well as space. And you do this like this. You write a function that starts with the name benchmark, and then you iterate over a certain number of iterations, which is determined by the compiler itself. So you write a for loop, and it runs it for times b.n. N is determined internally when you run it. And the output is interesting. It shows the number of, the amount of time it takes for each operation, that is each time the for loop is run, and the number of allocations you make in that operation. In this particular case, if you notice, I defined a variable called buff. It's an allocation for 1 million bytes. So as you would expect, yeah, because I'm allocating memory, there is obviously one allocation that is being done, right? Yeah, it's a very basic example. To correct this, I would probably recreate that variable outside of the for loop and recycle the buffer over and over again, right? And as you would expect now, there is zero allocation because I'm not doing any allocation inside the for loop. But the interesting thing is, the CPU time for each unit operation is now reduced by 20%. If you see here, it was 40,000 or 400,000 nanosecond plus. Here it's 310, 15 nanoseconds. Why do we get 20% reduction? There are two things here. One is there is one less operation per for loop, that is allocating. Malloc is not being called, and free is not being called inside the for loop over and over again. But also there is another thing. If you reuse the buffers, what happens? And this is how the keyword for is usually implemented in most languages. The way you do this is you create a variable and then you keep changing its value. Of course, same type. What happens is, all modern CPUs, they have caches, and by reusing the same variable and caches, because they implement LRU kind of algorithms, you always hit the same variable over and over again, thereby significantly improving your chances of reutilizing CPU cache and actually not going to RAM at all. Okay, the next thing that is very important when you write code belonging that is supposed to run as part of high throughput applications is how does it do I/O. Most applications which run for a long period of time would have to do some form of I/O, whether network or maybe storage or whatever. What really I/O is basically an operation that involves two things. You read and you write. In Go, there are interfaces for doing that. There is an IO.reader interface, which has a function called read, and there is a writer interface, IO.writer, which is a function called write. Pretty basic, right? And there are three modes effectively of doing that. One of them is what is called a buffered I/O, where you create, you allocate a certain segment in memory, and then you hold that thing, and once you finish operation, you pass it along. And there's another one that is streaming I/O, where you get some data, you pass it along, then you get new data, you pass it along, and so on. It's like a flowing pipe of water or something. And there's a special mode called piped I/O. It's basically used where you have a reader as a producer and a reader as a consumer. How do you connect them, right? While doing some operation in the middle. That's where pipe I/O becomes helpful, because it provides same kind of interfaces to two different consumers. Well, one producer and one consumer. And this has, the whole concept of streaming I/O is very common. Most people know it and most people use it, but it has some very interesting characteristics if you think about it. And especially in Go, there are so many structs and interfaces that are there, which provide so many different functionalities right off standard library, which are pretty amazing. And we'll go some of the use cases where you can utilize streaming I/O to maximize your memory efficiency. So let's say you're writing a web server, and it accepts certain amount of data. Let's say it's a file or maybe some long text data or whatever, or binary blob or something. However, you decide to restrict that, the amount of data you pass it on to me should not be more than X number of bytes or megabytes or gigabytes or whatever. How do you limit the amount of data you accept over your network? Because network is also a resource, right? You don't want to waste it. So by default, the I/O module has something called limit reader, which will return first n number of bytes that you define from any object. This is helpful when you, for example, you're reading a file and you just want, you think like, oh, the file, in a text file, the code that I'm looking for is in first, 100 lines or 1,000 lines. That's where probably this is useful, where you can, get some data and then, view it as string and so on. But in a real network-based application, how would you do it? So NAT HTTP also has a similar implementation, which is max byte readers, where you define, and you tell that guy that, I want just 10 bytes, 10 megabytes or something, and then if the request is longer than that, disconnect the connection or something like that. Now, why is this useful? So you would know that there's already content length header, which most of us use to determine what is the length of the request. But what if I'm a malicious attacker and I attack your server by saying, oh, it's 5 megabytes, but then I keep on sending, and if you don't have, well, Nginx and Apache and all those web servers usually have this thing, but if you are not checking for the length of the object that is actually coming in, then you are in for a very bad surprise. So that's where this kind of things come in very handy. Okay, another thing is something called MIME Sniffing. So you might have always noticed that if you implemented a web handler function for something like posts a file to your handler, you always would notice that when you test it from the browser includes a header called MIME type. Right, and you might wonder why is it included always, right? So browsers, like from the days of Netscape, they always check if the file type is valid for transmission and so on, and then they include the MIME type, which you can then use. But again, if I'm a malicious attacker to your server, I would probably say, oh well, you know what, it's just text HTML, and then I'll pass a binary or maybe SQL code that you might run, and then it's all gone, right? You might end up in a problem. So this is one of the things that, this is one of the ways to improve your security. But in order to do that, right, should you read the whole file that I'm sending you, or should you just read something? So there are various ways of doing it. One of the algorithms is mentioned in the citations, which you can use to, collect 512 KB bytes and then find out what is the MIME type, and then decide, should I accept this request or should I close it, right? And this is not based on the MIME type header, by the way. It actually looks for the particular signature within the byte stream or within the byte buffer to determine whether it's of type JPEG or PNG or it's a video, or if nothing is found, then it will tell you application octet stream. So one of the services that I've written is about uploading images, and I only want images. I do not want anything else. I could use something like this to determine whether I should continue with the request after accepting only the first 512 bytes. If it is valid, I continue, otherwise I disconnect it. And by the way, this is also there right in the standard library within the HTTP package. So there's a function called detect content type, which detects quite a lot of content types, but if you need more, there are also user packages that you can use. Okay, now once you have determined what is the content type, how do you continue? Let's say if you want to accept JPEG and I sent you a JPEG, now you have to continue, right? You cannot go back to the beginning of the stream. because you took out 512 bytes. So what you need to do is then you have a buffer and you have a stream which is already moved 512 bytes. Now you have to continue from 513th byte. So in Go, you have something called multi-reader, where you create a reader from the buffer that you're holding and then join the two buffers, join the two readers, the buffered reader and the original request reader. And it gives you a reader back from the beginning of time. So that's pretty cool because that saves you a lot of time. And everything, all of these readers basically implement io.reader interface, so you can replace any reader with any other reader. And that's how it's pretty useful. Okay, pipe reader. Like I said, if you have a reader interface and you have another reader interface, how do you do that? How do you combine them, right? You can use a piped operation wherein you use a pipe writer to connect onto reader 1, and then corresponding pipe reader goes back onto the other reader. So standard way of, a very standard example where you could use this, and this is something that most of the people would be doing in their services, returning JSONs from the objects that you hold in memory, right? So normally you use the JSON package, which gives you a buffered JSON. In most of the examples I find that, but it's quite funny. But JSON's encoder package accepts an io.writer interface. So you really do not need, you don't have any need to really buffer the output of this function. So what you could do is then you could pass a writer and then consume the corresponding reader into passing the data somewhere else, wherever you want to pass. Maybe writing to a response writer, which also accepts the reader, right? So this avoids creating any buffer in your application. This has a very particular use case. So imagine that you're writing a service where you need to handle multiple file uploads. Let's say the endpoint can be used by a user to upload several photos they take on their mobile device or something. And it's a post request, and it's a particular kind of post request. It's called multipart, which most people use to handle post requests. How do you ensure that you don't buffer anything? Because like I said, it can have n number of photographs, which means it can probably potentially go in hundreds of megabytes. And you do not want to use any more memory than what is needed. So what you do in this case is you create pipes, writer and reader, then you, and this is all done concurrently over two Go routines. The first Go routine accepts the request. The second Go routine writes to another request that you want to use for serving, whether it's storing on a block device, a storage device, something like S3 or something, or you have something like a transcoder where you convert the media that is being sent to you, any operation that you want to do on it. So Go has also something called multipart reader, which is again of the type io.reader. But the cool thing about this is it divides the multipart body into a number of parts, right? And each of the part is again of the reader type. And you can also create multipart writers, which are of type writer. And the cool thing here is, because I divided my original reader into parts, I can validate each and every part. By part, I mean each file which is represented as a part in your multipart request. And I can validate each of the file that you are attaching to it before passing it on to my consumer service, right? If something is not right, I can reject that part. I can do whatever. I can reject the whole request also, right? So that's pretty cool because I'm not wasting anything here. I am also saving network. I'm also saving the memory by not buffering anything over here. And yes, when I say that this is helpful in optimizing memory, I should also mention that you should close your I/O interfaces, because if you don't, then you are leaking memory again. Okay, there are some more interesting problems which are over here, but yeah, they are like off topic. So I included in the presentation, but you can go through them. You can retrieve the presentation if you like this kind of problems. They are there, and you can go, or you can ask me after the presentation also. Okay, the final thing is about context. There was a very nice talk yesterday. I want to add a little bit more to it. context in itself, more than a piece of technical information, it's more about an ideology. How do you use resources that you have? If you spawn your resources from request-bound sessions, what if the request bound session gets killed, or what if it gets terminated? What happens to the child jobs that you created, right? So that's where cancellation and deadlines come in really handy. But in addition, right, one of the biggest problems that it helps you solve, and if you do it right, are what are called Heisenberg bugs. Those are the bugs that appear suddenly in production, and then when you try to replicate it, it's gone. Context comes in handy, and standard way for doing it, which was presented yesterday as well. I'm just repeating the code here, but essentially it's the same thing. The only thing worth mentioning over here is so context also provides something called value, where you can store anything. But then when I propose that you should use context to solve the problem of unpredictable states, using context.value improperly can also introduce unpredictable states. So because it's, you could essentially think of it as a singleton pattern. So handle it with care. All right, so 4 things. You use escape analysis, do benchmarking, use streaming I/O, and use request-bound sessions where you need to keep track of the jobs that you're spawning off. And that should be helpful in optimizing performance on long-running services. That's it.
I'm sorry, Shams, but we won't be able to take any questions. We are running desperately out of time. So if you all have any questions, please catch him after some time. I hope that's okay. All right?
All right.
Thanks a lot.